Speaker is Maja Taskovic from the University of Texas at Austin, and she'll be talking about exponential tails for solutions to the homogeneous Boltzmann equation.
Thank you very much, and I would like to start by thanking organizers for having me here. It's an absolute pleasure to be in Rio, that's all I can say. So let's go to work. What I'm going to talk about today is joint work with Ricardo Alonso, who is from Rio, Irene Gamba, and Natasha Pavlovic, both from UT Austin. Here is a brief outline of the talk. It has 4 little sections. One is the introduction, then the statement of previous results, and then 2 of our results, one in L1 sense and one in L infinity sense. So the introduction. You heard a lot about Boltzmann equation in the past few days, and so by now you know that it models a rarefied gas in which particles collide 2 at a time. And the equation is an evolution equation of the probability of finding a particle at time t, velocity v, and position x. However, in this talk, I'm working with the spatially homogeneous Boltzmann equation, so we don't have x variable, just time and velocity. And in that case, the equation simplifies to this form. Q, as you already know, is a quadratic integral operator. And it can be represented either in a strong form, which you've seen already. So this is positive piece is the gain term, the negative piece is the loss term. Or you can look at it in the weak form by testing Q with some nice test function, using symmetries to represent it in this way. So what is going to be different from the mini course you've seen is how I'm going to define this kernel B. Okay. So my assumptions on kernel B are that it is factorized. So U is the relative velocity, V minus V star to some power gamma. And then there is an angular part. Okay. So for me, this parameter gamma is between 0 and 1, which are the so-called hard potentials. If you go to the negative side, there's the soft potentials. And this function B has a singularity at 0. And that singularity makes it non-integrable over the sphere. And that's a big problem when you do calculations. And so in 60s, Harald Gratz proposed to somehow ignore that singularity and just assume that the function is integrable over the sphere. This is just the Jacobian. And this assumption was accepted for a long time. And then in the last 20 years, there's been a lot of work without that assumption, and that's what we are going to do. So no Gratz cutoff for us, which means that this integral is infinite. But when you introduce an extra weight assigned to the r of theta, then the integral becomes finite. What this really means is that compared to the Gratz cutoff, this function B is allowed to have more singularity. R powers of more singularity. And ideally, you would like this R to be 2, so to give 2 extra powers of singularity. But we give ourselves a little bit of flexibility and allow R to be between 0 and 2. Okay? And so what is the problem we are looking at? We are studying the exponential tails of the solution. In particular, we want to know if they're created, meaning you start with some thick tail possibly, and then in a very short time, the tail becomes exponential, so very thin. Or if initially your tail is exponential, is it going to propagate in time? Okay. And you can do that in 2 ways. You can do it in L1 sense or pointwise sense. And therefore, these 2 norms are very convenient. So L1 exponentially weighted and L infinity exponentially weighted norm. So we want to see if these norms are propagated or generated in time. This is a little remark just to remind me to tell you that the exponential moment, or L1 exponentially weighted norm, can be also represented as an infinite sum of polynomial moments, just because you can use Taylor expansion and represent exponential function as a sum of polynomials, right? Okay. So that's what we study. And a little preview, just in case I run out of time. Main point I want to convey today is that if you show first the L1 propagation, then you will get the L infinity propagation. More precisely, we can establish the following estimate. So the L infinity exponentially weighted norm is bounded in a linear way by L1 exponentially weighted norm. So once you establish this and get the propagation of L1 norms, you will get for free the L infinity norms. Okay. Also, a little remark about weak versus strong solutions for Boltzmann. So when you do L1 theory, weak solutions are a natural setting. And the weak solutions, in particular the weak formulation, is very, very convenient to get the cancellation of that singularity of the kernel, okay? Because you can get it from your nice test functions. But when you deal with strong solutions, very little is understood about them. And in particular, some tools we are using require solutions to be so nice that we still don't know if they exist. So our results are going to be a priori at this point. And here I have two remarks. So one is that one of the tools when you deal with strong solutions is the so-called Carlin representation with some change of coordinates, going from sphere to a hyperplane. And another one is that, okay, so with weak solutions, cancellation comes from test functions, but in strong form, you don't have test functions. So where is the cancellation coming from? It's coming from a special splitting of the Q, and I'll show you that in a minute. And so what are the previous results? I always talk first about L1 because then L infinity follows. So L1, under the Graz cutoff assumption, it was Bobilev who first looked at the generation and propagation issues of exponential moments. And then there was a series of works by Bobilev, Gamba-Panferov, Gamba-Panferov-Villani, Mouhot, Alonso, Canizo, Gamba-Mouhot, among others. And altogether, what they proved is that when you look at the exponential moments of order S, and if that S is between 0 and gamma, which means that that exponential is pretty thick at infinity compared to the Gaussian, for example, then you can generate such tail. Okay. But if you look at S, which is between this parameter gamma and 2, so it means it's a little thinner tail, then you need more assumption on initial data, and the result becomes propagation. Okay. And that works for Graz cutoff case, and in non-cutoff case, Liu and Mouhot have an analog of this generation, so they show that exponential tails of order between 0 and gamma can be generated. But there was nothing beyond that. Gamma was in this potential rate, let me see here. This little gamma, okay, and that's a number between 0 and 1 for us. Good. So what we want to study here is what happens between gamma and 2. Can be extended as further as possible. And now about L infinity results. So essentially, there is just one paper, Gamba-Panferov-Villani, 2009. And they show that if initial data is pointwise below Gaussian, then it's going to remain below maybe a little different Gaussian, because this rate can be different, and uniformly in time. Okay. And you can actually learn quite a lot from their proof. For example, the strategy of that result was essentially the following. You first get the L1 exponential propagation, use that Carlin representation because you're working with strong forms, and then they show the comparison principle for the Boltzmann equation for the first time. And with these three, you get the L infinity propagation. And so now, if you want to generalize this to non-cutoff setting, okay, you need to take care of all these three things. So we are first going to talk about non-cutoff setting of the L1 propagation. The Carlin representation is fine in both settings, so we don't have to worry about that. But then there was a big problem with comparison principle, because the proof they had heavily relied on splitting the gain and loss, which you can do only if you have cutoff, not a stronger singularity. And so let's see about the L1 result. What did we do? What's happening? So a very classical idea when you deal with L1 exponentially weighted or polynomially weighted moments is to multiply your equation by the polynomial. By the way, this bracket is Japanese bracket, right? Square root of 1 plus v to the square. So multiply the equation by polynomial and then integrate in v. So what you get on the left side is really a derivative of the polynomial moment. And on the right-hand side, you will get a weak form of your q with the test function, which is polynomial. And using the symmetries, that transformed to this. And so now this b, remember, has that singularity we need to take care of. And that's going to come from these test functions, because if you look at the difference between v prime and v, there are a multiple of sine of theta, one sine. But then you do Taylor expansion up to order 2. And if you make a really smart change of variables, which some other people invented, then the first order derivatives are going to cancel out, and you get sine square, and it's perfect. Okay. Oops, not going to say much about this, but what are the new aspects? So the new aspect of our result is going to be that the order of exponential we can propagate depends on the singularity of the kernel. Okay, that was not the case in the Gratz cutoff. And another novelty is that we use Mittag-Leffler moments. So I just want to say briefly what are those. So as a quick reminder, this was the connection between exponentially weighted moments and polynomial moments. But the point is that instead of this q factorial, we kept getting the gamma function of aq plus 1. And a was non-integer. And then we was wondering, so what is this? Is it still telling us something about the exponential decay in the tail? And it does, because there are things called Mittag-Leffler functions, which are defined in this way. It looks very much like the exponential. If a is 1, it's exactly the exponential to the x. But if a is a non-integer number or any positive number, then this behaves asymptotically. This would be as x goes to infinity. It behaves asymptotically as exponential of order 1 over a. So there are nice test functions for us because they still describe the exponential behavior in the tail. And so we define Mittag-Leffler moments. So the statement of our result consists of two parts. One is with the most singular kernel, when this extra weight has a power 2. We reproduce a new proof of the generation for s between 0 and gamma. And we can get propagation for this s between gamma and 1. Okay. But then after that, proof doesn't work. So if you want to extend the propagation result, you need kernel to be less singular. So now we change the assumption and say, OK, let this extra weight be assigned to the r's of theta. And let's see, with that r, which is between 0 and 2, how far can we go? And what happens is that if you use Mittag-Leffler functions, you can go up to this number, which is 4 over 2 plus r. So if r is equal to 2, which is the previous case, you get 1, which was exactly the case there. If r is equal to 0, which is the Gratz cutoff, then you recover 2. You go all the way to Gaussian. Okay. But the point is that how far you can propagate depends on the singularity of b, at least with this method that we are using. OK. No proof there because I don't have time. And then L infinity, very quickly. So remember I told you now that we've dealt with the L1 propagation. We need 2 more tools, essentially actually 1 more because Carleman representation is OK. So it's the comparison principle. And what saved the day was a recent paper Luis Silvestre posted on arXiv in December, where he finds a way to bypass this problem by doing some kind of contradiction argument. And so his method uses strong solutions, very nice strong solutions. And the existence of those solutions is not known yet. So again, our result is going to be a priori for this part. And this is just a repetition that cancellation comes from the splitting of Q. So let's see how this statement, I'm sorry. First the statement. So assume 3 things. This pointwise behavior of the kernel, this nu is pretty much as R before, so it goes from 0 to 1. We cannot do up to 2. And assume that you have L1 propagation, which was already done in the previous theorem up to certain power. And assume that initially your function is below certain exponential of order s. Okay, good. So 2 minutes, right? Okay. Then the conclusion is that your solution stays below exponential of the same order, but maybe a little different parameter alpha. I just want to show quickly what is this Sylvester's approach. So what he says, and we had to modify to fit our setting, is just set as a goal that you want to show the norm you're looking at is less than this, a plus b to t to some negative number. Don't worry about that power. A and b are going to be found later. And for nice solutions, this norm is actually finite at every time, but you don't know how it behaves in time. So this estimate is going to give you a control. Now, because initial data has finite norm, and because this norm is continuous in time, this estimate, and this guy blows up and t is equal to 0, this inequality is true at t is equal to 0. And because of continuity, it's actually true for a small time interval. Good? And so assume that this inequality doesn't hold for all times, and let t naught be the first time where this fails, which means where there is equality. And that means the derivative of the difference is positive, which comes to this, and you do algebraic manipulation, and you get a lower bound on the derivative of f. So to contradict this lower bound, you use that this partial t is equal to q, and then you look for the upper bound of q, which is going to be lower than that. And that's going to be your contradiction. And so to do that, you have to split q. The typical splitting of q was this, because the f prime minus f gives you the cancellation, but that wasn't good enough for us. So we had to split it further. And it was this way. I cannot tell you much more. I'm out of time. I just want to say that the negativity, which is always an issue when you deal with Boltzmann, comes from the first q1. The estimate on that guy is negative, and the other two guys are positive. But the negative guy has highest power, so it's going to win all over. And when you put it together, you get the contradiction, and you get the L infinity propagation. Okay, that's going to be faster. And thank you.
Any questions for